Hello everyone, and thank you so much for coming, and thank you very much for having me. It's a great honor. Roland, you showed all the pictures of the previous awardees, and it's a real delight and pleasure to be here. I'm showing this because I have multiple ties to Sweden, and one of them is this little book, as well as its author, Astrid Lindgren. She's really famous, at least in the German children literature. And so my son, who is with us, Paul, he just finished this book. It's one of his first books he finished, so I thought I'd show this. My title is Go East. I'm referring to efficiency, accuracy, scalability, and transferability. Roland immediately knew the cultural reference here. If you don't, it's a pleasure to look at it. It's worth a brief YouTube excursion. I'm really interested in a first principles view on chemical compound space, and I don't think I need to motivate this for a long time, but here's my one slide motivation. This could really help us to accelerate the time we need from materials, ideas to market. And this is maybe less well known, but similar to pharma, this takes typically a decade with the current methods, and the hope is we could accelerate this a lot by making use of physics, computer simulation, robotic experimentation, data analysis. So Bifold is a center at the Technical University in Berlin and other institutes. So there are major efforts to push this field. It's one of the reasons also, maybe the reason, why I recently decided to move to University of Toronto. There's a strong commitment towards pushing this direction, which is centered around the Acceleration Consortium, which is led by Alana Spoor-Gutzig, who is one of the previous Löwdin lecturers. So the world is small. And this also in combination with the Vector Institute, which was founded by Geoffrey Hinton, one of the founding fathers of machine learning, if you wish. So we want to bring all these things together to solve chemistry, right? This is the purpose at the end of the game should be to accelerate chemistry. And the alphabet of chemistry, we all know. For some strange reason, it's taught relatively late in the children's curriculum. I had to discover, and then also by recollection from my own school curriculum, I have no idea why, right? This is an alphabet like the alphabet we learn in preschool, and why don't we learn this alphabet as well? I don't understand this. I think it's maybe partially responsible for societal analphabetism when it comes to chemistry. I think it could be. But anyhow, so 3 years ago, it celebrated 150 years since Mendeleev, and it even got an article in the New Yorker, right? So I truly admire people who publish chemistry papers in the New Yorker. This is, I think, the most prestigious journal of all for science. Maybe you don't know, but there are alternatives to the current, the conventional way of portraying the periodic table. And these are beautiful, and they are not wrong, right? These are just alternative ways, other projections of how we can order the elements. I'm not sure about this one. This seems suspicious to me, but the others look fine, and these two are also fine. And so it's a little bit the question, how should we arrange the alphabet, right? It's an arbitrary order, of course. And you know this if you change to languages with other alphabets, they have completely, with other languages, they use completely different alphabets. In particular, there's an order which should be interesting to us. This is Pettifor's David Pettifor from Oxford, he introduced this numbering scheme to those of you who don't know. And if you reorder by following these lines, the elements, then it turns out that a property like the heat of formation of solids becomes linear in this property, right? And in this ordering. And so if you wanted to calculate this property, right, accurately, it would be really a major challenge, right, from scratch. But yet, if you just have 2 points here, it's close to trivial to invert, and you could design your material. And so this is a little bit the underpinning of my entire talk. I carry this belief, right or wrong, that chemistry is actually much simpler than it formally ought to be. Experimental chemists will sort of agree to this, but the formal scaling, I think, is much worse than it typically has to be. And so I try to work out a little bit in our research efforts, we try to work out why this could be the case. Now, there's more recent work on this, right? It's ongoing, so here's a paper from Hardy Gross and Miguel Marquez exploiting this, but still you can only get so far if you project things down to one dimension, right? That should also be clear, and maybe one dimension, maybe chemistry is simpler than formally necessary, but also one dimension might be oversimplifying things. Anyhow, so the typical world we live in, and the previous speakers, of course, worked a lot in this, and going beyond this simplified picture is this Pareto front of force field, semi-empirical, Hartree-Fock, MP2 or quantum Monte Carlo, couple cluster methods that become increasingly more accurate, but typically you have to pay for it, right? So you have to be rich to be accurate, and these are just ballpark numbers for atomization energy, so quantities an experimental chemist might care about, so the strength of the archetypical binding, right? These are errors you might or might not find acceptable. If you manage to push this Pareto front down, right, then you're doing a great service to the community, right? Obviously, you're making, at the same cost, you're delivering more accuracy, or at the same accuracy, you're delivering much more cases one can study. So we are pursuing 2 philosophies in this direction. One is based on the statistical learning theorem, so this supervised learning, given some input parameters and output. So in other words, Hamiltonians or systems, external potentials, so number of electrons as well. I omitted this, assuming charge neutrality. You get quantum observables, and most importantly, the energy, but also other observables. And if you have enough of those, you can train a regressor and then infer the corresponding observable for new examples. Right? And so this is possible in chemical compound space, and I'll come to that in a moment. And of course, that's also our first speaker this morning referred to some of that. Our other approach is based on perturbation theory, and also this was a topic of today. So in some sense, you can view this here on this cartoon. Imagine you've solved the Schrödinger equation for this point, then you can expand in these solutions and make predictions on the same surface for any other observable, or also towards other surfaces, right? So you can include in your perturbation also nuclear charges and not only geometrical displacements or external fields, and that would then give you a prediction on a new compound. And this is quite a rather old idea, but it's a little bit niche, so it's not very broadly used. And what you can see quite easily is if you look at the Hellman-Feynman derivative, your first order expansion within density functional theory, this then becomes an expansion and derivatives of the electron density, which is removed by one order. Right? And so it's quite intuitive to see how systems change into each other. And so this is to make things a little bit dramatic. It's not as bad as that, at least not in my lab, but you could think about that these are seemingly contradictory, but I think it's two sides of the same coin, right? And in one case, you're interpolating using training examples. In the other case, you're Taylor expanding. Now, starting out with these alchemical Taylor expansions, consider the case of N2, this is the N2 molecule, as a function of its distance, the electronic energy, so the energy without the nuclear repulsion, right? It's a monotonically decaying function towards the fused atom, right? The 7 proton of the 2 nitrogens piled upon each other. This is 14 protons, this is aluminum, right? And that's the limit of this red line, right? Actually, also, if you fuse CO, it's also photon. It's also silicon, right? It's always, so this is a 14 electron, 14 proton system, right? And the electronic energy goes towards that constant. But you can also look at the shape as you vary the nuclear charge distribution, right, in this. I'm in my wildest dreams, I'm thinking about making this all quantum, right? Maybe that's possible. I'd love to explore this idea, but so far we are just treating this classically, right? So it's the classic external potential, typically also within pseudopotentials. But you see there's this, due to symmetry, right? There must be this kind of concave shape. And so it's quite natural then to ask what's the Hessian of that? So we have a generalized Hessian here. And here's a nuclear charge, second order derivative. You can normalize, diagonalize this, and these are then the normal modes. And these 2 normal modes, they span, it's like a basis in your chemical space, right, for all these diatomics with 14 electrons, right? So this is the fixed, so I'm totally orthogonal to our previous speaker. We can extend this to multi-atom systems. Then the symmetry of the surface is not trivially by rotational symmetric. And you see here the normal modes of the nuclear charges in benzene, and they look like Hückel, right? And this is actually clear. It's a 6x6 matrix with off-diagonal elements corresponding to some interaction, and all these matrices result in these kind of normal modes. And you can expand any, these are now BN-doped benzenes, right? So any carbon-carbon pair can be changed into NB, charge conserved. All these mutants can now be described by a linear combination of these 6 normal modes. Right? So that would be, again, my argument, right? This space of all mutants collapses into a basis in which you can easily expand things. With the corresponding eigenvalues, you can estimate then the energy. So that's the blue line here. And you see it follows nicely the trend of what's going on here. Those are the energies, but of course you can also do this for electron densities. So as I just said, this is the Hellmann-Feynman derivative. If you differentiate it further, you can build first, second, third, fourth derivatives in the electron density. You pile them on top of the electron density of N2 and you recover CO or even BF if you change one nuclear charge further, right? And these electron densities, they compare very well with the actual SEF densities, right? Now, I'd like to tell you about something we recently discovered. It was published just last year in Science Advances. I couldn't tell yet many people about it because of the pandemic, but I'm really excited about this. And we think we have discovered a new symmetry relationship in chemical space. We call this the alchemical chirality. So to understand this, let's look at benzene. You perturb it to Bn. It looks something like this. This would be your perturbing potential, the perturbation in Hamiltonian. This is your unperturbed electron density. And this is now your first order perturbed density, second, third, and fourth. But I can push this further, right? So if I took this molecule and I flipped it around, right? So if I perturbed instead of to nitrogen here to boron and here to nitrogen, obviously it should be the same system, right, by rotation asymmetry. But if I perturb it once more, right, this one here versus the perturbation the other way around, where you say NBBN, that's no longer obvious by rotation. You cannot superimpose them, right? So in this case, your perturbing Hamiltonian would look like this, and this is your first order perturbed density. And now if I add the corresponding mirror image in terms of opposite perturbation, you see I just have to flip the sign. So it's the same perturbing Hamiltonian, it's just antisymmetric, right? And then the electron density perturbations here, if you look at them, they look exactly the same, right? Now, it turns out that this is an odd function, and if you multiply it with this perturbation density, it cancels out. So you're sitting on a ridge here. Your first order derivative is 0. But the second order derivatives, they also happen to cancel out. And you can see this if you look at the difference in energy of the two Taylor expansions, either to this enantiomer or to that one. You can factor out the perturbed densities, and then you see that these two happen to have the same sign, and then by going in one direction versus the other, they cancel out exactly, right? So up to third order, these are exactly degenerate in the electronic energy. And then you know immediately there's an inequality from the nuclear repulsion. You know immediately who's lower and who's higher in total energy. You can also see immediately that bonds, if I start counting bonds in these molecules, in this isomer I have NN and 2 BC bonds. Here I have a BB bond and 2 NC, and I have a CC and 2 NB bonds. But if I compare then these two, they cancel, right? And I can then solve for the NC energy in terms of a BC bond energy plus half the difference between the homolytic bonds. So I have a rule for estimating bonding energies, new rules for bond energies. So you can generalize this. Of course, it's not restricted to carbon and Bn, right? You can go anywhere in your periodic table. So we have a QRS elements, any adjacent elements. You could estimate the SR bond as the QR bond plus half the difference between the homolytic bonds. So we wanted to see how well this does actually numerically. And we went to this paper. They had published DFT-based bond energies for single covalent bonds. And so you can predict, of course, to the left, right, going QR to the left or to the right, so in either direction. And those are the filled symbols for the second and the third period. You see this here in blue. The mean absolute error is 7 kilojoules per mole with this simple model. And you can extend this also by saying you calculate the bond to the right, and then you use that calculated value as the reference value to calculate the bond to the right again, right? And this is what we mean by recursive. So the empty symbols are the recursive ones. So all the empty symbols were obtained. All you had to provide was once the starting bond, and then you can go through the entire periodic table without any QM calculation or any experiment, right? So it's a general. These are back on the envelope sort of cost. You can also rank molecules then by nuclear potential between these alchemical enantiomers. And we did this for all possible naphthalene derivatives. There's more than 2,000 in here. And so we did CCSD calculations to get a good QM estimate for all these 2,000. That gives us the QM rank. And then we have the alchemical chirality estimate rank. You see, it's quite decent, right? It's separated by the stoichiometry, right? So it's a bit like a phase diagram of mixture in stoichiometry. And then we can compare to the rank other methods would give us, right? So universal force field would be giving this rank. Bond counting is the blue one. PM6 is this this purple one. Then we have the A's, so this alchemical chirality is this orange line, and just a little bit better is XTB. And now just think, I mean, XTB is amazingly sophisticated by comparison, right? You really need a computer to run XTB. Maybe bond counting is as simple as this ACE, and in terms of numerical complexity. And then if you wanted to get really better, then you'd have to move to proper SVF. We also wanted to push this further. We looked at over 4 million Piscean derivatives. Right? So we could consider all these stoichiometries shown here. There's up to 11 carbon-carbon pairs in here. So 11 BN is fully doped. It's only BN, no carbon, right? Here there's one CC pair. We didn't do 9, 8, and 7 because they're just too many. It's this combinatorial explosion. But we can rank them all because it doesn't cost anything. And then, of course, we don't have the quantitative energy estimate, but we can look what features show up when in the rank, right? And then we know what features affect stability. So it's a statistical argument. But basically, based on this, we find that as you add BN pairs, you stabilize this thing. As you add BN pairs, as you maximize the number of CC bonds, as you substitute preferably on sides shared between rings, so these kind of sides rather than sides that are not shared. If you maximize the BN bonds, if you avoid N substitutions on rings sharing a large amount of bonds with other rings, and so on, right? So you see these trends here. So this basically tells you it's the frequency of BN counts, right? So here you see many BNs for the lowest ranked isomers. Obviously, you can immediately print out the least stable or the most stable for every composition. This is all done without a single QM calculation, based simply on the inequality derived from the symmetry. Of course, this is not limited to 2D. This is the diamond crystal, and these two systems, if you were to dope this diamond crystal this way, they should also be degenerate. So it's an approximate degenerate, but this also works for other systems. So here's an example of a trimere. You take mangan, free mangan, you perturb it, the top one, you perturb it twice to the right, and then the other two ones to the left, right? So that would be one perturbation, and if I go now the other way, I have this cluster, and they are supposed to be degenerate, right? So I know, without doing a QM calculation, they are roughly the same. Obviously, I can repeat this game then anywhere I wish in the periodic table, right? So we wanted to push this further, and with the student Michael Sare, who is still at University of Vienna and now under the group of Laetitia, we wanted to explore this further and see if we can compare this to MO theory and valence bond theory. And so in particular, the rule of Linus Pauling for estimating bond energies was what we had in mind. We wanted to see, can we do something similar here? And so we base things on the DFT because everything we do is perturb the electron density to get there. So we can grow these atoms, right? In a bond, we can grow one or the other one. We can look at these trends and we can print out how the energy changes as you change the nuclear charge of one atom then. And so based on such curves, we arrived at an expression for the bond energy which looks like this. So the energy between atom A and B is a constant, minus this product of the nuclear charges, plus a sum of the nuclear charges raised to the 7/3. And so Marcus previously pointed out on the Coulomb matrix, the diagonal term, this is Z to the 2.4. This comes actually from, it's similar to the Z to the 7/3. And in the limit of very large Z, this becomes a very good estimate of the energy of the free atom with all the electrons. So basically, I have the energy of free atom A and the energy of free atom B, right? So That's basically how we can interpret this. And you arrive at this expression by simply looking at the numerical calculations of these alchemical transforms. And so we wanted to test this, and these are now calculations from Michael Sache. He went through all possible combinations of the bonds in the second period, in the third period, and in the fourth period. These are all single bonds, right, covalent bonds, and we saturated it with hydrogens. And you can then do this for carbon bonding to carbon, nitrogen, oxygen, fluorine, nitrogen binding to nitrogen, oxygen, fluorine, etc., etc. And you see there's quite a decent agreement actually with DFT and our model, and the agreement is actually better than Pauling's agreement, right? And Pauling, you have to know also, so we fit 3 parameters to the entire period. So this is depending on the period, also B and C are depending on the period, but much less. But Pauling has something fitted on every element, right? The electronegativity. Now you can of course argue that's not a fit, but I don't know if it's an observable. Maybe we have to talk about this. Anyhow, so of course there are also limitations to this. Just 2 remarks on this. If we push things into the 2s shell, then this parabolic kind of ansatz, right, obviously breaks down then, right? So this is not going to work. And also one remark, if you differentiate with respect to nuclear charge, then you recover something which really looks like the Hammett equation. Right? If you recall Hammett from it's something an experimental chemist called Hammett came up with this nearly 100 years ago, that many properties like equilibrium constants or rate constants would behave like a product ansatz. So one parameter which would go through chemical space, and the other one would be the slope for the reaction. And so we find different slopes for different periods, and then the number of valence electrons or the effective nuclear core potential becomes what goes through chemical space. You can push this alchemical expansion further to also relax geometries, right? So everything I've shown you before, we sort of neglected geometry. And of course, as you change composition, you might want to include the relaxation effects. And in this paper just from 2022, with Giorgio Domenichini, who is another PhD student who's still in Vienna, he's in physics. We showed that you can actually not only predict the energy but also the gradients, and then use those gradients on even Hessians on the predicted other surface to estimate where the geometry should go. Right? And so he tried different ways to make this work. Turns out, as one would expect, that the Morse potential gives you better estimates. And here you see some predictions for paths as you go from methane to ammonia to water to HF, and as you deprotonate again, you can see in these arrows, so this arrow is the prediction of the angles in the error on the angles in methane using NH3 density and derivatives and so on, right? And the orange one is to predict the structure of ammonia starting from methane, right? And so you see we get decent agreement with angles. This the bond length error you make is in millibor, so pretty good. And the energy is, of course, also improved as you include relaxation. To probe this further, we also looked at all these benzene derivatives, which we doped, right? This is now, again, the same list of doped benzenes. And you see the vertical alchemical estimates, as well as these relaxed ones, and they come much closer to target. Here you see the error plot, root mean square. So this is Hartree, right? So here you see milli-Hartree and Bohr again. So with this, I'd like to switch gears now and change to the machine learning stuff. This was started out in a program I organized at the Institute of Pure and Applied Mathematics in 2011. It was called the Navigating Chemical Compound Space for Bio and Drug Design. And Markus actually was a speaker at this meeting. Klaus Müller and Alex Tkachenko and Matthias Rupp were also there. And so Klaus Müller is a machine learning chair at the TU Berlin. And so I pestered him with this question, look, why do we have to solve the SCF for every new compound from scratch? So Parinello, Kai and Parinello showed already that for different configurations, you didn't really have to do it. We knew a lot about this, but as you change composition, you would always redo things. And so at the time, we had these high throughput DFT campaigns starting. And so it was a burning question. And so I proposed this now a cartoon of the Coulomb matrix. That's what I proposed to try as a representation. My reasoning was really, if you think about how you represent a molecule, right? What is the molecule, right? In easy terms. So Marcus also pointed this out. It has the descriptor has to be easily accessible, right? Then I thought, well. You want to account for interactions, right? If there's no interaction, it doesn't exist. So atoms interact, and the easiest interaction I came up with is the Coulomb interaction, right? So that's what we put, and then there were all these index invariance issues and so on, which led to the diagonalization. But we also use this kernel-rich regression approach. It's consistent with the Gaussian process regression, and so you have the closed form solution for the regression coefficient. In practice, you don't fully invert this matrix, right? You just solve the linear system of equations. Anyhow, the cool thing really, I believe, which really convinced me at that time was that the error is known. It must decay inversely with training set size. And there's mathematical proof for this, that the leading error term must decay like this. And so from this result these learning curves. So you present the log of the prediction error as a function of the log of the training error, and then offset and slope will determine the data efficiency of your model, right? And so this is a straightforward way to compare also different models, right, in a systematic fashion. And so that's really then one appealing aspect, and the other one is that when you do your prediction, you don't have to do the training anymore. So you shifted the investment upfront before the training and into the data acquisition. So you can acquire the data, or you take it from somebody else, and then once the model is trained, predictions are very fast. So we've shown that this works for QM properties in chemical space, first in 2012. And then in 2013, we repeated a little bit the exercise for other QM properties and using neural nets. So this is, as far as I know, these were the first papers doing this in chemical space. So for us then a big question was how can we improve these learning curves? How can we improve the models such that they show improved learning curves, right? So with lower offsets and better slope, and how can we avoid such behavior, right? And we've identified more or less three really important aspects of machine learning, which is, one is how you represent your system. The other is how you connect it to other methods, legacy methods. And the third is how you select your data, right? And we've been working on all these fronts at the same time, but I think roughly speaking, those should be combined ideally. And so I'd like to tell you about something we did to address this last thing first, and then also something about delta machine learning, which is sort of the most straightforward way to do legacy methods, to include legacy methods. So in this selectivity issue, right, it's this question, how do you train? If you wish to make a prediction, how should you train? And there's a huge difference, it turns out, if you know what you want to predict beforehand or not, right? And that is it's sort of obvious to the atomistic simulation person, but I feel in many cases it's not disclosed in the most explicit ways, but it makes a huge difference. And so let me explain this a little bit further. Suppose you wanted to predict a big molecule like this. The naive machine learning approach would be, well, I need many other big molecules just like that to train on, and then I can make a good prediction here, right? That's the the usual paradigm which you have, and from that comes the statement: the bigger the data, the better. Right? Now, by being smarter about your selection, you can get away with much less data, but the condition for this is that you know the query molecule beforehand. If you know the query molecule beforehand, then you can get away with much less. And the way you can do it is by training locally, right? So another condition is that your property must be extensive, right? And so the energy is, but so it doesn't work for all properties this way, but for those that are extensive, your training atoms can be, the number of training atoms can be much smaller than the number of atoms in your query system, right? And so, for example, you start training for this hydroxy group by including a training set which starts out small and which grows in environment, but which will never be as big as the entire system, right? And in this way, you can basically construct a library of fragments. And you can train on those fragments which are most relevant to your training. Now, that of course implies that you're sort of training on the fly, right? So once you're given the training, the query, only then you start acquiring the data tailored to your query, right? Now, if the method is efficient, that training on the fly can still be at an acceptable cost, and you can enjoy a great speed up. So the way this works is, if you have some training, you go through the graph and you find all the subgraphs to identify the fragments. This is not necessarily a condition that these have to be graphs. You could also work with coordinates of subparts. But that's how we started it out. For this query system with 9 non-hydrogen atoms, these are the fragments of the graphs going up to 7, right? You see it's a very, very small set of molecules. When you train in general randomly for such a big molecule with 9 atoms, you would require something like 1,000 other organic molecules at least. Here now you have something like 50 molecules, right? So a much smaller set of training molecules, and also the training molecules are much smaller, right? So if you are using QM methods to get the energies, right, that's also going to be much cheaper. And you see the error now on the atomization energy shown in black here. It becomes smaller, and then as you increase the size of your training fragments, you're approaching 0 from above, so this designed error. Then you overshoot, and then you're coming back, and so at 7 atoms, so including this bag here, this bin of fragments, you're at less than 1 kcal per mole error deviation from the reference QM value for this molecule. So on average, we find, if you do this, repeat this for many queries, right? We find that on average, you need less than 100 molecules of these fragments in your machine learning model to train to make the prediction, right? And your prediction error comes down like this. So we are showing the variance here as vertical and horizontal lines. So we built up a library of small fragments. We call them amens. This is an animation with the 1,000 smallest amens, right? So these would show up again and again as you predict other organic molecules. And if you compare this to a randomly trained model, which should be applicable, so then you use only one model for all molecules, right? Here you use only one, for every molecule you use its own model, right? But this is the difference in slope you can then enjoy. Here you see an application to large molecules such as Taxol or LSD, and you see as you increase the number of atoms in these fragments, in these amens, your error drops down to the diagonal line where you'd like it to have. On average, the mean absolute error on these is shown in brackets here. So you see even with just size 5, you get only 10 kcal per mole error on average, and that's what a good GGA would give you, all right? You see up here statistics on how frequently these fragments are used as you go through compound space, right? So for any organic molecule, there's going to be a carbon, a methane fragment, right? That's going to be in every organic molecule by definition, so you have it everywhere, right? So that one you can recycle again and again. But you see, as you increase the fragment size, they become less and less frequent in chemical space, and so you don't need those, right? So we're enjoying here an exponential decay in terms of what we need for training, while at the same time, the number of molecules for which we could query this fragment database, that number grows exponentially, right? So I'd argue that's a win-win, right? If what you're paying for goes down exponentially, where you can use it, it grows exponentially. So most recently, we've put out a dictionary of 140,000 amines going up to size 7. And with this, you should be able to predict any zinc or GDB molecule, right? Most recently, we've tried to get to QMC level of accuracy within a collaboration with Argonne National Lab. Anwar Ben Ali, he's been using the supercomputers there to run QMC calculation with QMC Pack. And he did this for the amen for this dictionary here. But we couldn't afford to do it for 140,000 molecules. So he only did it for up to 5, right? And that's already over 1,000 molecules he did with QMC now, very carefully converged. And then to validate the power of this database, he also did 50 large molecules. These are the QM9 molecules. So these all have nine atoms. We've selected them at random. And these are now the learning curves. If we predict directly on the B3-lib energies of these, so these are diffusion Monte Carlo numbers for these molecules. And then we build an Amen delta model, which connects B3-lib to quantum Monte Carlo, and that works very well. And so with amens only up to size 5, you really come close to 1 kcal per mole in terms of predictive accuracy. We can analyze these errors. Where do the big errors in amen predictions come from? And these are now these 50 molecules, the errors of them. And we picked one which has a big error, number 7 here, has a large error. And if you look at it, you see there's a delocalized pi system involving more than 5 atoms. So our largest amen has only 5 atoms, right? And so there's no amen that represents really this system. But if you go to number 27, very small error, you see there's also a similar system, only it has 5 atoms, and there the error is more. Right? So that's how we understand these, what the machine is trying to tell us. Finally, I'd like to touch back again on this point of the selection and on the small effective dimensionality of chemical space, right? So also these amens, right? Such a small number, only 1,000 amens for which you need a high level accuracy, and then you can cover a lot of chemical space. It would suggest a very low dimensionality. And so we wanted to explore this further. And so we asked this question: if you know your query already, if you're query aware, how should you train a machine, right? And there are different scenarios where you could have this. You could imagine this, that, for instance, say you have identified an extremely promising drug candidate, but before you want to go through the effort to synthesize it, you would like to know its toxicity, right? But you don't have its toxicity data. It wasn't synthesized yet. But maybe you have toxicity data of compounds that are close by. Right? In such a case, you should use the toxicity data of the molecules close by rather than the largest toxicity machine learning model which was trained for any possible chemical. Right? So rather than going for the generic one, you should pick the smaller model, counterintuitively, the model which was trained on less data, but more relevant then. Right? And so this is what we do. We first rank by similarity, and then we train the model only on the nearest neighbors. So suppose you want to predict this guy, you only train on this nearest by. And then it turns out, if you compare this to a model which was trained on everyone, you're consistently below and better, right? And so we tested this for the harmonic oscillator. You train nearby, you get this, this improved machine learning model. Also the Rosenbrock function, a 2D function, we tested nearby, and you see this. We can then look actually at the dimensionality of the system by using this trick. We use the radius which we find, how far you have to go to get to an acceptable accuracy, right? And as you add more training data, that radius becomes smaller and smaller. In other words, you're increasing the training density, right? Now, if you do a log-log on this and you rearrange for your number of training instances and you make this a variable, you can fit the density, right? And you can fit the intrinsic dimensionality of your underlying problem, right? And in this way, we find that the intrinsic dimensionality for the harmonic oscillator is not 1, but it's rather 0.6, and for the Rosenbrock function, it's 1.5. Now, we repeated this exercise for molecules.
Did we run out of battery?
Hello? Oh, no, I just switched it off. I'm sorry. So you can repeat this for molecules, and these are now QM9 molecules, and each time you know your query, and you select those nearest by, and then depending on how large the pool is from which you select your additional similar molecules, you see that you converge towards the random machine learning curve for the largest pool from which you can draw, but you're systematically below the non-aware machine learning model. Here's an example for 2 cases that had the most extreme radii, so the largest and the smallest, and this is how the density would grow, right? So think about it like an onion in chemical space. You're adding more and more molecules which are further and further relevant, and at some point your machine learning model will no longer profit from having more molecules being added. And so we can do again the trick with the dimensionality, and then for these organic molecules we find that the dimensionality is below 2. So we don't really know what this means, right? But it would suggest that it's much below the former scaling. Now, another thing you typically find, especially talking to mathematicians, they will say, oh, it's all a high-dimensional hypersphere, and so on the sphere, it's so high-dimensional, everything is orthogonal. We wanted to test this, and actually it's not true. You see this, we tested the orthogonality of various representations, but what you find is that this would be sort of the random, the infinite dimensional inner product, while if you take the actual representations of actual organic molecules, you find a distribution like this. So it's clearly not as bad as the former scaling would suggest. Okay, we have some examples then, how if you ordered some drugs and you had to develop a drug in a business case, you could save a lot of cost by making use of similarity models, and it's also very general, so we even applied it to real estate problems. So estimating the cost of purchasing an apartment in the city of Berlin, you would also be advised not to use the generic model, but rather a model that was trained for your specific, in terms of similarity to the apartment you're actually looking for, right? With this, I'd like to conclude, so I hope I could tell you a little bit and convince you that there are relations in chemical compound space which we can exploit. There's a certain structure. These are recent review papers we published. I have to thank the many people who did all of this work, in particular Bing Wang, with whom I developed the Amen method. And these dimensionality discussions were done with Dominic, and here you have Mike Assar, and actually here's Giorgio for the alchemical relaxation. And I'd like to thank you for your attention and happy to answer questions.
Thank you, Anatole, for a very interesting talk. I guess there are some questions in the audience.
Everybody's exhausted.
It's getting late now, so
we need beer.
I was wondering, when you create these fragments, do you sort of terminate with hydrogens, or how is that?
Yes, of course, yeah. Sorry, I should have mentioned that. Yeah. We do that. Yeah.
We have one first there, and then.
Can I go? Yeah. Thank you very much. I was actually wondering something similar, but the fragments in these or these amons, do you optimize them, or is it sort of knowing the query that you sort of fragment that particular configuration of it, or how does that work?
Yeah, this is an excellent question. If you know your query, the best thing for your query would be if they are not optimized, but actually constrained towards the geometry in your query, right? But then, of course, they become less transferable to other queries. So that's a trade-off, actually. And so in our dictionary, we just brute force relax them. And that means that then if your query has some strained geometry, and that's also something we see actually in our studies, you need to have a larger amon that actually captures the strain of your local geometry. Yeah. But it's true. Ideally, you would have an amon dictionary also with constrained geometries, and we believe that would be much more powerful. But then, of course, that dictionary would be much larger. Yeah. But great point.
Yeah. Thank you for a very interesting talk. More fuzzy concepts such as aromaticity, you had Asabora naphthalines and Asabora benzenes. Would it ever be, or can you say something about predictions of aromaticity in those?
So what I've showed, this symmetry, this alchemical chirality, has nothing to do with aromaticity. It's completely general, right?
Yeah.
I don't know. I'm afraid I don't have to say anything about aromaticity.
Okay. Because it can be.
No, it's we don't find it to be crucial for these derivatives, right? It's just part of your electron density, so it's implicitly present, right? And it might actually reduce a little bit the need for relaxation because it keeps things more in place. But other than that, we haven't particularly looked at it.
Okay, thank you.
Do we have any final questions before we leave the word here? Yeah.
This is just a quick one about nomenclature. Because I saw in one of your last slides that you now switched to quantum-based machine learning, whereas you said quantum machine learning on your Angewandte piece. And I think it's just a confusion with quantum computation connected to machine learning. So did you change now? Did you change the notation for this? Are you calling it now quantum-based?
No, I don't like to be married to notations and these. No, but you're completely right. There's a little bit this danger of confusion. But my argument is always that we use quantum Monte Carlo to describe classical Monte Carlo on quantum objects, or quantum molecular dynamics, like ab initio MD, right? Doing classical Newtonian dynamics with quantum forces and so on. So I figured we use the same for what we do with machine learning, mostly also to distinguish from the more traditional bioinformatics approaches you have in the pharma world, right? But of course, there's this confusion with people doing quantum computing with machine learning. So far, I haven't really. So we were in touch with some quantum computing people, but they thought their finding on our kernel-rich regression problem was that it would not be accelerated if you had quantum computers. So maybe this will go away in the long run. I don't know.
So with this, I think we should thank both speakers from this session.